All right, so I've been trying to think about how I would implement rollback networking, and one of the questions that has bothered me is how to synchronize the tick numbers between two peers, so that when you receive input for, let's say, tick number 6, you can roll back to tick number 6, inject that input, and roll forward, and it will only work if my tick number 6 is the same as your tick number 6. And I've been following this article on Gamma Sutra where the author sets up this like local lag, remote lag, and advantage thing to allow peers to skip ticks when they go out of sync and then come back into sync. And I think I have it working, which is just what I want to show here really quickly. So here, we'll make this one be the server. I'll set up this one to be the client. I'm doing a client-server thing rather than a peer-to-peer thing just because it's easier to set up, but it doesn't really matter. It's just two machines talking to each other through whatever mechanism. All right, so you can see each one gets a little window for the other peer. So here, this is the server. It's talking to remote peer, blah, 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 this ID. RTT is the round trip time. That's how many milliseconds a message to go there and back. Here's the tick counter. We're counting these ticks. The local lag and remote lag. So local lag is how many frames that we are simulating locally, that we're predicting locally for the remote client. So that's like how many frames are we ahead of what we've received from them, and remote lag is the reverse. We're calculating how many frames they have predicted for us on their side. And both of those calculations are done based on passing like tick numbers back and forth, but they aren't dependent on the other one actually telling the other one what the lag is. So they're calculated independently on both sides, and right now they're kind of flashing back and forth really fast, which makes it hard to tell. But for most of the time, they guess each other's reverse numbers correctly, which is heartening. The advantage is using those numbers to see how many frames ahead of us, or actually, let me think about how this works. It's how many frames behind us the peer is, because being behind gives you an advantage because you're predicting fewer frames. And it's this advantage number that it's using to decide when to skip a frame. So right now, nothing's being skipped because we're running on localhost. They're staying really, really well in sync. They're only predicting, or theoretically predicting 1 or 2 frames. There's no actual prediction going on. It's just passing these packets with the tick numbers enough to do this calculation. But theoretically, you'd be passing in each of those messages the inputs, and then using those, injecting them into like our buffer of inputs and predicting for the ones we don't have, blah, blah, blah. So now let's see what happens when we introduce some artificial latency. We're going to introduce 100 milliseconds of latency. And you see the round trip time goes up to 200 something because latency times 2 is round trip time. And you can also see the local and remote lag have jumped up. They're now 7 or 8. So we'd be predicting 7 or 8 frames. And on this side, we actually saw that the other client got 2 or so frames ahead, or I should explain what I mean by ahead. So it's the difference between the local lag and the remote lag. So it's fine if I'm predicting 8 frames and you're predicting 8 frames. That means that we're still running pretty much in lockstep on our independent computers. It's just this latency in between that's causing us to predict these frames. But if I'm predicting way more frames than you, then that means you have an advantage because you're getting all of my input and I'm not getting any of your input. So that's why we're calling this advantage. But really, it just means that that one host has fallen behind. So the disadvantaged host is going to start skipping frames. So we skipped 1 frame here. 100 milliseconds of latency really isn't that big of a deal. It just means we're predicting more frames. But like we got back in sync really quick just by having this one-time skip a tick. And I'm sorry, I should be saying ticks always instead of frames, but I kind of got in the habit of calling these like simulation frames. But we'll say they're like they're ticks. They're simulation ticks. Anyway, 100 milliseconds of latency, not a big deal. Let's do 100 milliseconds of latency with 2.5% packet loss. And this just goes crazy. Like, look at these numbers. Like, the local lag and remote lag will spike up to like 20, 30, 40, which is just nuts. So just a little bit of packet loss, 2.5% packet loss, and you have to start predicting like a ton of frames. We also see the advantage numbers going way up. So down in the messages here, so the max advantage, it's called max advantage because it's imagining multiple peers being connected. So you would take what is the highest advantage of all of the peers I'm connected to, and I'm going to skip frames based on that, which might actually take you too far with some of the other peers. But then they, on their end, will detect that an advantage has gone to you, and then they will start skipping frames, such that theoretically, if all of the peers like skip the appropriate number of frames for the max advantage, we'll reach some sort of equilibrium. Anyway, yeah. This is really crazy, but really cool. Like we see there was a max advantage of 14, so we skipped 7 frames, max advantage of 4, so we skipped 2 frames. On both sides, every once in a while, we're having to skip frames because due to this packet loss, we're predicting more frames for each other. The difference between how many frames we're predicting on both ends is getting out of sync, which means that we need to slow down so that we don't just, have one running way ahead and another running way behind. So that's really cool. I just can't believe how little packet loss causes a big problem. So let's restore everything back to 0 so we're not introducing any latency or any packet loss. And you can see they quickly reach in equilibrium 2. When the latency goes away, one side will again end up with a big advantage, and then they just skip enough frames to get back to where they need to be. If we just introduce, let's say, 250 milliseconds of latency, but with no packet loss, and like this isn't even that big of a deal. The round trip time gets quite high, around 500. We're predicting like 15 to 17 frames on either side. This is at 60 frames a second, so that's still a fraction of a second, which is a lot. It's a lot, but except when there's like really intense maneuvering going on, you might not even be able to notice that. And if it's a fluctuating 250 milliseconds, it's not always 250 milliseconds, maybe jumping from 100 to 250 and kind of back again, like that could kind of work. And it doesn't even have to skip very many frames to stay in sync. It's really, well, this would be a better test if it wasn't on the same machine, right? Machines that would perform a little bit differently, and if they weren't just passing numbers, if there could be an occasion where it actually took a machine like longer to simulate a frame than usual, that would be a really good test, because then we'd be able to see how this would respond. But yeah, like even let's do, can I make it do only packet loss with no latency introduction? Let's try that. I'm not super familiar with this feature of the Linux kernel I'm using here. Let's see if this works. We'll introduce 1% packet loss with no latency changes. So it accepted my command, and not much has changed. We've stayed about the same here. Let's introduce way more packet loss. Let's go up to 2.5. So yeah, that gives us kind of spikes in round trip time, occasional spikes in round trip time. I haven't noticed if it had to skip any frames, but yeah, that's not bad. Like somehow this combo just of like latency and packet loss like really does a number on like let's just add a delay, a latency of say 25 milliseconds. That's super minor, but with the 2.5% packet loss. Okay, that's not that bad either. Like the local lag and remote lag spike occasionally from like 3 to 7 or 8, where I think the 3 is just from the 25 milliseconds. And we're skipping frames occasionally, but that's not that bad. It's just that combo, I guess. 100 milliseconds latency and 2.5% packet loss is a big deal. Anyway, I just wanted to show that because I think this is actually working. I think it's actually keeping the tick numbers in sync between these two clients, which could theoretically be used for rollback networking. So it's still a lot of work to actually implement rollback and make that work, but I feel like having this problem solved makes it so that I can more easily imagine how I would do the rest of it. So that's it.